Hello, we are Team 8P2, and today is December 5th, 2019, and this is our 251 final design project. Our team consists of Matthew, Jeffrey, Helen, Dylan, Simon, and Nachiket.
Before we could begin designing a rocket vehicle, we first needed to define the stakeholders' needs and requirements. Beginning with the stakeholders, we defined the probe transport and operations team, the aircraft team, the zombie apocalypse survivors, and the Purdue campus population. From these stakeholders, we defined needs. We needed communication, an available transport vehicle for the probe, the ability to find survivors, the ability to relocate survivors, develop a minimum cost for the probe deployment system, and a quick relocation system for survivors. Finally, we derived the requirements from these needs. We must be able to carry a 20-kilogram payload. The launch facility must be able to support a multi-stage system. We must minimize orbital decay. The propulsion system must be able to reach the Kármán line. We must be able to launch within 2 to 3 years. And we must have the minimum number of stages required to get into orbit.
For our risk analysis, we use NASA's risk analysis matrix with consequences on the x-axis and probability on the y-axis, both rated from a scale of 1 to 5. This was used to calculate the impact of each possible risk. So, for example, if a sensor were to fail, the consequence would be catastrophic, a level 5, and the probability would be moderate, a level 3, making our impact a 15. Our mitigation for this risk is to add redundant sensors that act as a fail-safe in case of sensor failure. For our concept generation and selection, we came up with some propulsion system requirements. We require that the propulsion system have a minimum number of stages, thrust-to-weight ratio of greater than 1.4 for the launch stage, and greater than 0.1 for subsequent stages. It achieve required delta V. It also have the ability to carry the required payload, and it also should use heritage launch systems. We also defined criteria to evaluate these requirements, and including minimum cost and inert mass, high ISP, maximum safety, low failure rate, minimal toxicity, a thrust-to-weight ratio greater than or equal to heritage launch systems, and the minimum amount of stages required.
This weighted decision matrix was used to consider all of our initial concepts for a propulsion system and then choose the best 3 to do a more in-depth analysis. We weighed 8 initial concepts and compared them using our propulsion criteria and mission requirements. The top 3 were multi-stage solid, multi-stage hybrid, and multi-stage liquid as seen in the table.
The delta V achievement for each propulsion system as number of stages increases is shown in the bar graph on the left. Also seen in that table are the ISP, F inert, and M pay for each propulsion type. On the right is a chart of the staging characteristics of each propulsion system, including delta V, M prop, and M inert for each stage.
After adding the staging characteristics to the propulsion criteria and mission requirements, we reanalyzed our 3 propulsion types and determined that a 2-stage liquid rocket is optimal for our mission.
Once we knew our rocket was a 2-stage liquid, we selected our fuel type, which was RP1 with a liquid oxidizer for both stages due to its convenient availability on campus. The ISP for typical liquid bipropellant is shown on the right.
Once we knew our propellant, we calculated our gross mass of the rocket and used historical thrust-to-weight ratios to determine the thrust required for our rocket. The thrust required for each stage is shown in the top table. We then selected 3 engines for our propellant to determine which would be optimal. But as can be seen by the red highlighted values, the engine mass would be greater than the inert mass, which isn't possible. Therefore, the Rutherford was the only possible engine for stage 1, and a Tri-D was the only possible engine for stage 2. Our final structural and propulsion system design specifications are shown in this table. The statistics for the length, diameter, material, and fin maneuverability have been added, as well as the burn time, shutdown process, and stage separation system. This gives us a good picture of what our system is capable of, while also giving the characteristics of it.
In this project, we learned to make sure that team roles are explicitly assigned, that communication and accountability is key to success, that doing more peer reviews would help with our holistic success, and that intermediate deadlines would help us ensure steady progress. Our sources are included at the end of the video.